So, we wrote an equation which is f u equal to some u is equal to cos theta and f u equal to u double dot. Now, we examined the root, we started examining the case where f u dot equal to 0. So, essentially we were looking at the roots of this polynomial which is f u, and we essentially what we did was we set f u equal to 0 and tried, we argued that the roots or we argued that at very high u or very low u, f u will be going to positive infinity and negative infinity. And we have also seen that u equal to plus minus 1, this term uniformly vanishes for u equal to plus or minus 1, leaving behind this term which is a negative definite term. Now, for this negative definite term, it will definitely have negative value at u equal to plus 1 or minus 1. So, what would be the possible shape of u in f of u in this region, whether it would be like following the green line or it will be following this red dot, that we have to examine, right. So, but before that, let us try to understand it more in a physical consequence. What is this f u equal to 0 means? So, essentially what we did was so if you recall, the original equation was f u is equal to u dot square. So, we essentially set, when we put f u equal to 0, that essentially means u dot equal to 0. What does it physically signify and what are we looking for by examining the roots of f u equal to 0? So, let us look at it in a more physical manner. So, there are three types of possible motion in a symmetric top. The first motion is the spin motion. So, let us say this is my top, I am just drawing this top like this. We have a disc and we have forced a massless rod through the disc, for example. So, we have, this is my space. So, now we are describing all the motion with respect to the space set of axes. Okay. So, this is my x prime, this is my y prime, this is my z prime, right. So, the first possible motion is the spin motion of the top, spin at around its own axis, which is given by let us say a spin velocity omega s, right, or we can also call it omega z, that is up to you. Now, in terms of Euler angles, please realize that omega s is very well represented by the last Euler angle's time derivative. So, omega s is your psi dot, right. So, this is one motion of top, which is the spin motion, which is very nicely taken care of by the third Euler angle. Now, there are two other motions possible. If we trace the top axis, the axis of this top, okay, and we see how it behaves with time as the top spins. If you recall, a child's top, it also rotates around its own axis, and this rotation is so if I just draw it separately. So, this is my first case. Now, for the second case, here I am only drawing the axis of the top, okay. I am not even drawing this disc, okay. So, if we follow the tip motion of this tip, so it also rotates around the space z axis, okay. So, this is my x prime, this is my y prime and this is my z prime. So, the axis of the tip of the top also precedes around the z axis. Now, this precision, if I draw it in if I project it in the xy scale, it will be kind of a closed motion. I am not saying it is a circular motion, I will just say it is some kind of a closed motion in the xy plane, which is very well described by phi, is not it? Because we have a motion which is around the axis, around the space z axis, and if you recall our initial discussion on Euler angle, the first of Euler angle phi is a rotation around the space z axis. So, this angle phi is very well describing this particular type of motion. So, we see that the second of the motion which is called, okay, so let us give the name. So, this is my spin motion. This motion is called the precession. It is called the precession motion. Precession means when the axis of the top rotates around the space z axis. So, all these axes are space axis, here and here. Okay. And the third one, the third type of motion is called a nutation. Nutation is when you have, let us say, your axis system, once again x prime, y prime, z prime, and your, I am just again drawing only the axis of the top. Okay. So, what happens is this top with time it falls or goes up. So, essentially it can, let us say, come down to this position. Okay. So, it can come down, I mean, make an angle theta 2, or it can go up to make an angle theta 1. So, essentially the this axis can move up or down with respect to again the space z axis, and this, so that means it is a motion which is well represented by the motion of the second Euler angle, which is theta. Okay. So, if you recall, the second Euler angle was a rotation around the modified x axis, which is once again can be represented looking from the space set of axis is. So, if some object, I mean, if some axis is moving up and down in this direction, this can be very well be represented by this theta, okay, this particular Euler angle. So, we see this nutation is represented by theta dot, I mean the nutation velocity is represented by theta dot, whereas the precession velocity is represented by phi dot, whereas spin we have already seen is represented by psi dot. So, 3 Euler angles in case of symmetric top represents 3 types of motion possible in a top, right. And I think we probably nutation is obvious when you are looking at a child's top, nutation is very obvious. Precession is also obvious, I mean nutation is not very obvious, but if you look carefully you will see that when the top is rotating, it is not, first of all it is not exactly vertical, it is slightly tilted. Of course, you see this precession frequency, I mean precession motion. Spin, of course, it is obvious, if it is not rotating it is not working. And finally, the nutation when it goes up and down, it is not very obvious, but sometime you might have seen it if you have played enough with a child's top. Well, I did, so I could easily identify all these 3 motions. Okay. Now, let us try to understand this once again. Now, when I say u dot is equal to 0 in this in the expression of f u equal to u dot, okay. So, if u dot is equal to 0, if you recall, u dot is equal to minus sin theta dot. So, if this is equal to 0, we can either have sin theta equal to 0, which implies theta equal to 0, okay, because theta is what? Theta is this particular angle. It can, so that means the axis of the top remains totally vertical along the z axis. Now, that is a very special case. So, we will just keep this aside, I mean we will discuss this case, but we will not now, it is a special case, we will call it the slipping top, we will come back to that. Or what we can have is theta dot equal to 0, that means there is no nutation motion, okay, so there is no, essentially no nutation motion, right. Now, if we set theta, or rather it is not about nutation motion, I would say if during the motion, if it encounters a turning point. So, what I mean is, see, if the axis of the top is moving between 2 limits theta 1 and theta 2. So, for any theta which is greater than theta 1 and less than theta 2, less than equal to theta 1 and theta 2. Okay. In this, for this theta, the top motion is possible. Let us assume for a moment that this is the range of nutation. Now, if this is the case, then the axis of the top or when the axis of the top reaches theta 1 and theta 2, that means it has to change the direction. It can go up to here, and as it reaches theta 1, it has to start coming down again, because this is, see, where to get this range, how to get to this range I mean that's something we will discuss later, but let us assume that this is the range which is defined physically. Now, if this is the case, that means it has to go, I mean the top has to go up, then it comes down, then as it reaches theta 2, it once again starts coming up. So, these are the turning points. So, theta 1 theta dot equal to 0 means these are the turning points of the nutation motion. For precession, it is not a bound motion. When we talk about the precession motion, which is the rotation of the axis, it is not a bound motion. So, this is there is no upper or lower limit. So, theta dot equal to 0 means there is no precession motion. Okay. Similarly, spin is also not a bound motion. Spin is about its own axis. When we say psi dot equal to 0, that means there is no spin. But for nutation, theta dot equal to 0 means it is the turning point of the nutation motion. When the axis goes to certain limit, it turns back, and that's at that point theta dot equal to 0. Of course, we can also have theta dot equal to 0 if there is no nutation motion. That is also a possibility, but what I am trying to tell you that theta dot equal to 0 need not necessarily mean that it is not a nutation. I mean there is no nutation motion. It can also mean it is one of the turning points of the nutation. Now, with this knowledge, let us come back to this one. Now, what is u essentially? U is equal to cos theta, and that is how, so let us, u is equal to cos theta. So, that is how u dot is equal to minus sin theta d theta. Now, we have treated u, when we were examining the roots of f u equal to 0. Okay. So, we have treated u as a continuous function, okay, and that we had to do it because you see the leading term of this function, this polynomial is u cubed. So, it has 3 roots, right. So, we know that if it is a polynomial of order 3, then it has 3 roots. If it is a polynomial of order n, then it has n roots. Out of that n roots, maybe m number of roots are real, and there could be n minus m number of imaginary roots. Okay. So, this is all comes under the theory of polynomials and all, and so some of you might be familiar with it. But what we know immediately from this, if the functional dependence of f u is that there has to be 3 roots, and from the physical consideration, and so looking at the functional form, we see that the physical range of motion of u is between +1 and -1, right. So, if cos theta equal to 0, what is the physical range of cos theta? Okay. So, now let us come back to this once again. Where is it? Here. So, what is the physical range of cos theta or physical range of theta? Theta can vary between 0 and 180 degree, right. So, theta has to be theta has to be within this range. So, that is to say 0, theta, pi. Now, in this range, cos theta can have a value of 1. Okay. So, when we check the range of u, so it has to be between 1 and -1. So, that is for any physical possible motion. Please remember u is equal to cos theta. So, u has to be within this range. Now, we see that from the consideration we have, from the functional form we have for f u, there has to be one root which is above between u equal to +1 and positive infinity. That we have seen in the last class itself, because otherwise this cannot be satisfied, that when u goes to positive infinity, this goes to infinity, u goes to negative infinity, this has to go to negative infinity, and when u equal to +-1, this has to be negative definite. These 3 conditions tells us that one of the roots of u has to be imaginary. It cannot be visualized in a real world. Okay. So, this is our, we call this root u3, and the other 2 roots u1 and u2. For any physically possible motion, it has to be between +1 and -1 in this bound. It has to be within this bound. So, the shape, from this physical argument, we see that the shape is actually this, not this, right. So, we have intersection points with the u axis, and these are called the roots. These are the roots of the system. The third one we already called it u3. So, let us call this u1 and u2. So, we have 3 roots of u, out of which one is imaginary, 2 are real. So, u1 and u2, that corresponds to these 2 theta angles, theta 1 and theta 2. Okay. So, we from this, if we try to correlate these two discussion, for the physical motion of the top, it has to be between u1 and u2, but please remember cos theta and cos theta, with increasing theta cos theta decreases. So, the limit of theta is between 0 and pi, and limit of u has to be between u2 and u1. So, u1 is greater, u2 is less. Okay. So, these are the physical range of u in which we can have a motion, physically possible motion of the top. Clear? Right. So, now let us try to explore the so what we have seen so far is, so what we have done here is we have set u dot equal to 0, these are the turning points. From there we just followed a physically possible, I mean we followed an argument to find out 2 physical possible routes of the top motion, and these are correlated with these 2 angles theta 1 and theta 2 in the nutation. Now, also there is an additional condition, if you recall, this additional condition is f. So, one condition is f u, which is equal to 1 minus u square alpha minus beta u minus gamma minus delta u whole square equal to u dot square. Okay. So, this is one relation we have. The second relation is phi dot is equal to gamma minus sorry, just give me a second, what is it? Yeah, gamma minus delta u divided by 1 minus u square. Okay. So, this is the second relation. So, let us focus on these 2 relations and see how does the top motion, that axis of the top or tip of the axis of the top behaves in space when we set certain initial condition in terms of phi dot and theta dot, or basically the initial conditions, we set certain sets of initial condition and see how this motion takes place, right. So, let us come back to this. Phi is the precision. Okay, we have seen that phi is this motion, right. So, let us assume that initially we are releasing the top from a certain angle theta 0, which corresponds to u equal to u 0, for which we have initial condition. So, this is at t equal to 0, okay, at t equal to 0, theta equal to theta 0, which corresponds to an u equal to u 0, and when we are releasing, so it is like this, let us assume that the axis of the top is rotating. So, it is spinning, of course. So, if there is no spin, there is no motion. So, if it is spinning and we are just holding the tip, so let us say this is the origin, this is the point where it touches the origin. Okay. So, it spins around its own axis and you are holding the top at this position, then this angle which it makes with the vertical is your theta 0 angle, and that means there is no precision, right. So, you just release it from that point. So, what happens is it starts falling, and then at the same time when it starts falling, okay, so if you write down the energy equation, total energy is kinetic energy plus potential energy is what? mgl cos theta. So, when it starts falling, cos theta increases, that means mgl cos theta, the total potential energy contribution decreases. As it decreases, it has to gain, I mean the total energy has to be constant. So, if that has to be done, so there has to be some additional kinetic energy. To gain that additional kinetic energy, the precession motion is triggered. So, it starts moving sidewise, moment it touches the lower limit, it goes up. So, as it starts falling, the nutation is already there. Okay. So, then the precession motion also starts and it keeps moving like this, executing all three motions. Of course, it has to do spin. Without spin, nothing can work. So, it has to have spin. Additionally, moment we start, just from physical argument, we can see that it starts precession and nutation together, right. So, the initial condition is at t equal to 0, theta 0 equal to u and phi dot equal to 0. Of course, we can have initial condition when theta dot is also equal to 0, but we are not taking this as a general case. So, I will show you a short video later on gyroscope, which is also an example of symmetric top. I will show you how we can have cases where phi dot equal to 0 and theta 0 is still not equal to 0, right. Anyway, so right now this is a special case. So, in general we are just considering at theta t equal to 0, theta equal to theta 0, which is corresponds to u 0 and phi dot equal to 0. Substituting in here, we get u 0 is equal to, or delta u 0 is equal to gamma, right. Now, which means, so if we substitute this here in this equation, if we write it down, u dot square will be equal to 1 minus u square alpha minus alpha minus beta u minus, okay. So, if I do this substitution, it will be gamma times, sorry, delta times u 0 minus u whole square, which is a new form of Fu. Now, anyway, so this is not terribly important. What is important is, if I now, okay, so similarly we can write phi dot to be equal to gamma minus delta u, which where delta is gamma u 0. So, we can write this as gamma u 0 minus u 1 minus u square, right. Now, let us assume that during the motion of during the top motion, it is the axis is hitting a, so we start at a position which is higher than the initial bound of theta, I mean the smallest of the angle of the initial of the bound in theta. What I mean is, we can release the top, okay, I will just draw it again, maybe that will be easier for you, okay. So, this is my axis x prime, y prime, z prime, all the discussion in terms of space frame, I am saying it over and over again. So, let us assume that these are the angles theta 1 and theta 2, which are two bounds of the nutation motion, and your u 0, it could be u 0 or theta 0, it could be, so we have cases where theta 0 could be greater than, or rather less than, both theta 1 and theta 2. We can have a case where theta 0 is in between theta 1 and theta 2, right, or rather I will just use this. So, it can be between theta 1 and theta 2, it can be less than theta 1 and theta 2, it can be equal to the upper bound, right, it can be equal to theta 1, but if it is equal to theta 2 and starts falling from here, or if it is less or greater than theta 2 and starts falling from there, then the top motion is not physically possible. So, three physically possible regimes are theta 0 is equal to theta 1, theta 0 is less than theta 1 plus theta 1 and theta 2, theta 0 is in between theta 1 and theta 2, and third one is theta 0 is equal to theta 1, which is less than, or less than theta 2. So, these are the three possible physically possible initial condition. What happens once again, what happens if we have theta 0 equal to theta 2 for example, or greater than theta 2. So, let us consider this. We have, let us say this is my value of theta 2, right, which is the lower limit. So, it can oscillate between the axis of the top can oscillate between these two limits. You start initially at theta 2. Now, moment you start, it starts dropping. So, even if it drops, if you start at theta 2 already, even if it drops slightly, it is it is outside the physically possible motion range. So, the top falls. Similarly, if you start below theta 2, it anyway falls. So, the physical consideration tells you we can have only 3 types of motion in this 3 initial condition. Now, let us carefully examine the signs of phi dot at different limits for this 3 initial condition. So, okay. So, phi dot is equal to gamma u 0 minus u 1 minus u square, right. So, when case 1, when theta 0 is less than both theta 1 and theta 2, right, which corresponds to u 0 greater than both u 1 and u 2, right, because theta and u, their kind of, their trend is kind of opposite to each other. So, if this is the case, then at both the limits u 1 and u 2, phi dot becomes positive greater than 0 at both u 1 and u 2. So, you have a precision speed at both the limits u of theta 1 and theta 2 to be positive, right, and what you get is the axis of the top. Now, let us switch to the screen here, computer here. So, the axis, see, this describes the first case where theta 0 is less than both theta 1 and theta 2. So, we have in the both limits precision speed greater than 0. So, that means the if I am like tracing the top of the tip as a function of time, so the top, because it is a fixed length, it has to be on a sphere. On the sphere surface, if I mark theta 1 and theta 2 like this, so my theta 0 is somewhere here. So, theta 0, which is unfortunately not marked here, is up somewhere up here, right. So, theta 0 is less than both theta 1 and theta 2. So, so the top starts falling initially from an angle which is less than theta 1, settles between these two limits, and we have positive velocity, positive precision speed at both the limits, and we have a trace is something like this. So, it keeps moving like this. Okay. Now, if I take the second condition, which is theta 1 less than theta 0 less than theta 2, which corresponds to u 1 greater than u 0 greater than u 2. So, phi dot, so if you see u 0 is less than u 1, right. So, that means phi dot is less than 0 at theta 1, phi dot is greater than 0 at theta 2. So, that means you have a precision which is positive at the lower bound, but negative at the upper bound, which corresponds to the case, second case. So, you start from a position which is between theta 1 and theta 2, let us say some initial angle which is lying between here. So, your top starts, let us say from this point, starts falling initially, has a positive velocity at the lower bound, but when it goes up and hits the upper bound, it has to hit the upper bound because these are the two physical possible routes, physical possible bound. The phi precision speed is negative. So, it goes slightly in the opposite direction, starts falling again, and then it keeps moving like this, right. So, we have a situation where we have a trace which looks exactly like this. Okay. Now, let us move to the, let us go to the third case, which is theta 0 equal to theta 1, that means u 0 equal to u 1, and of course, we have u 2 which is u 0 greater than u 2, right. Fine. Now, in this case, phi dot is equal to 0 at theta 1, phi dot is greater than 0 at theta 2. So, we have a precision which is 0 at upper limit and greater than 0 at lower limit, and we have a situation just like we have in the third case. So, it is a cusp, this particular shape is called a cusp, 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 okay. And so, this is the trace. So, you might have been already, if you are looking at the textbooks, you might be familiar with these shapes, and many of you will find it extremely difficult to understand what are these shapes physically mean. So, these are the physical interpretation for these shapes, okay. So, all this can be taken out, I mean all can be understood in terms of this very simple mathematics, where we only we first find out the roots by setting f u dot equal to 0, okay, and then we slightly modify this equation for this particular initial condition to this, and all these three conditions or all these three types of traces are direct consequence of this simple mathematics, right. Okay. So, this is more or less our discussion, I mean general discussion on symmetric top. We have two more cases of fast top and spinning top, fast top and slipping top, and we will finish that and that will be the end of the rigid dynamics officially. Of course, you can always write me your questions if you have any. I am obliged to answer the question. So, after this we have one more lecture on rigid dynamics, then we will continue with topic of Lagrangian dynamics. Thank you.